Look at a block of wood. It appears completely continuous, solid, unbroken. But zoom in past the cellular structure, and that continuous reality disappears. You enter a vast, dark void, populated by infinitesimally small, constantly vibrating spheres. Every physical object in the universe is built from these discrete units. Scientists call this material matter, and to classify as matter, a substance must satisfy two strict conditions. It must occupy physical space, meaning it has volume, and it must have mass. For centuries, early Indian philosophers categorized the physical world into the Panchtattva, 5 basic elements comprising air, earth, fire, sky, and water. Today, we understand that to explain everyday phenomena, why ice melts, how perfume fills a room, or why sweating cools skin, we have to look past the surface. We must derive the physical rules of matter from the bottom up. The solidity of a rock, the fluidity of water, and the temperature of the air around you are not intrinsic, unbroken properties. They are simply macroscopic illusions generated by the collective behavior of billions of invisible particles. The first rule of this particulate model is that matter is highly porous. There are vast empty spaces between individual particles. This animation illustrates exactly how that spacing works. When you dissolve salt into a beaker of water, the overall water level does not rise. The crystalline structure of the salt breaks apart, and each individual salt particle slides precisely into the pre-existing empty voids between the water particles. The second rule governs the physical scale of these particles, which is far smaller than standard human intuition can easily grasp. We can prove this scale by dissolving just 2 or 3 tiny crystals of potassium permanganate in water. Even if you dilute that solution repeatedly, taking a fraction of it and moving it into clean water 5, 6, or 8 times, the liquid remains visibly pink. A single crystal is dividing itself into millions of distinct units, spreading through the new volume over and over again. Matter is not a solid block. It is a massive, highly porous grid of unimaginably small, distinct units interacting across empty space. These units are never at rest. Every particle in the universe is in a constant state of motion, meaning it possesses an intrinsic amount of kinetic energy. This autonomous movement leads to diffusion, which is the natural intermixing of different types of particles. The rate of this mixing depends heavily on particle mobility and density. If you drop ink into water, its high mobility allows it to spread rapidly, whereas a dense fluid like honey diffuses much more slowly. This vector animation shows the direct mathematical relationship between thermal energy and particle motion. Notice how the velocity arrows lengthen dramatically as the digital thermometer beside them rises. If you drop a crystal of copper sulfate into hot water, it diffuses significantly faster than in cold water because the added heat directly increases the kinetic energy of the particles. But kinetic energy isn't the only factor at play. The third rule of our model is that particles continuously exert an attractive, cohesive force, pulling each other together. The strength of this internal bond varies entirely based on the material. A piece of chalk shatters easily under slight pressure. A rubber band stretches but resists breaking, and an iron nail easily withstands the blow of a hammer. The particles inside the iron are bound by a massively stronger force of attraction. The physical state of any material is just the outcome of a microscopic tug-of-war. Heat acts as the accelerator, pushing particles apart, while intermolecular forces act as the brakes, holding them together. When intermolecular forces win that tug-of-war, the material takes on a solid state. Solids possess a definite shape, a fixed volume, and a rigid structure because the particles are locked closely together. When kinetic energy increases to loosen those bonds, the solid becomes a liquid. Liquids maintain a fixed volume, but lack a fixed shape. Their particles have enough space to slide past one another, allowing the material to flow freely as a fluid. This split-screen animation demonstrates what happens when kinetic energy fully overcomes the attractive forces, resulting in a gas. Gases have neither a fixed shape nor a fixed volume. Because of the vast empty space between gas particles, the piston effortlessly compresses the gas, whereas it encounters heavy resistance against the liquid and complete gridlock against the solid. This extreme compressibility is highly practical. It allows us to pack huge volumes of liquefied petroleum gas into home cooking cylinders, store concentrated oxygen for hospitals, and compress natural gas to fuel vehicles. Because gases are so diffuse, their particles easily slip into the spaces between liquid molecules. Atmospheric oxygen and carbon dioxide constantly dissolve into our oceans and rivers, providing the exact mechanism that aquatic animals rely on to breathe underwater. Solid, liquid, and gas are not permanent identities. They are merely temporary physical configurations, dictated entirely by how much space exists between the particles and how freely they can move. If you push this particle spacing to physical extremes, you encounter states beyond the standard three.
The fourth state of matter is plasma, which consists of super-energetic, highly excited ionized gases. You see plasma in everyday life. When an electrical current flows through a sealed glass tube containing neon gas, it ionizes, glowing vividly. This ionized state also occurs naturally at cosmic scales. The extreme temperatures inside the sun and other stars rip electrons away from their nuclei, creating the glowing plasma that illuminates our solar system. On the opposite end of the thermal spectrum lies the fifth state of matter, the Bose-Einstein condensate. This state is formed by taking a low-density gas, a fraction of normal air, and cooling it to near absolute zero. The existence of this ultra-cold state was first predicted mathematically in the 1920s, stemming from calculations made by Indian physicist Sachendra Nath Bose, which were later expanded upon by Albert Einstein. Pushing temperature to either absolute zero or millions of degrees shatters standard molecular behavior, forcing particles to adopt entirely new, extreme macroscopic properties. Returning to standard Earth conditions, the boundary line between a solid and a liquid is the melting point. This is the precise minimum temperature required to convert a solid into a liquid at atmospheric pressure, which for ice sits at 0 degrees Celsius, or 273.15 Kelvin. Similarly, the boiling point is the exact thermal threshold where a liquid gains enough energy to transition entirely into a vapor state. This animation illustrates a crucial thermodynamic concept. During a phase transition, like melting ice, the thermometer stays locked at 273 Kelvin. The continuous thermal energy does not raise the temperature. Instead, that energy is consumed entirely as latent heat, or hidden heat, used exclusively to break the intermolecular forces holding the solid lattice together. Once the lattice breaks and the liquid state is achieved, the temperature rises to the boiling point and locks again. Here, the energy is absorbed as the latent heat of vaporization. Because vaporized particles absorb this massive amount of hidden energy, steam at 100 degrees Celsius causes significantly more severe burns than boiling water at the exact same temperature. Some materials bypass the liquid phase entirely. The direct transition from a solid to a gas is called sublimation, while the reverse is deposition. Solid carbon dioxide, widely known as dry ice, sublimes directly into a gas the moment it is exposed to normal atmospheric pressure. Temperature is not merely a subjective measure of hot or cold. It is a strict physical metric that dictates whether applied thermal energy is currently accelerating particle speed or tearing structural bonds apart. This side-by-side animation highlights the structural difference between boiling and evaporation. Boiling, on the left, is a bulk phenomenon. Particles from the entire volume gain enough energy to vaporize, creating chaotic bubbles at the heat source. Evaporation, on the right, happens completely below the boiling point. It is strictly a surface-level event, where individual high-energy particles break away from the top layer and escape into the air. Because it is restricted to the top layer, expanding the exposed surface area, like spreading out a wet towel, directly accelerates the rate of evaporation. Increasing the ambient temperature further speeds up the process by giving more surface particles the kinetic energy they need to escape. Environmental factors play a heavy role. If the air is highly humid, it is already saturated with water vapor, creating a bottleneck that drastically slows evaporation. Conversely, high wind speeds continuously clear away local moisture, allowing the surface particles to escape much faster. Evaporation is not a chaotic bulk disruption like boiling. It is the quiet, continuous departure of energetic particles from the liquid surface. When those surface particles depart, they take a significant amount of energy with them. To complete the phase change into a gas, they must absorb the latent heat of vaporization from their immediate surroundings, leaving those surroundings physically depleted of heat energy. If you pour a few drops of acetone or perfume onto your palm, you immediately feel a sharp, intense cold. The liquid is acting as a thermal vacuum, pulling heat energy directly out of your skin to power its own evaporation. This is the exact mechanism that keeps water surprisingly cold inside traditional earthen pots during summer. Water continuously seeps through the microscopic pores of the clay and evaporates off the outer surface, draining latent heat away from the water stored inside. Desert coolers exploit this evaporative heat theft by operating in hot, low-humidity environments to maximize cooling. It also explains why humans wear cotton clothing in the heat. Cotton is a highly efficient absorber. It pulls sweat away from the body and exposes it to the open atmosphere, facilitating rapid evaporation that actively drains thermal energy away from the skin. The relief of a cool breeze, a cold earthen pot, or a breathable shirt isn't magic. It is driven entirely by the invisible thermodynamic theft of latent heat, by the discrete, constantly moving particles of matter that surround us.